In this brain tumor detection project, we'll be looking at how AI can be used for improving the outcome of healthcare, especially in diagnostics. So here we will be developing or modeling an AI system which is trained on various brain MRI images. In some images, the patient do not have any problem. In some images, the patients have some kind of brain tumor, and often it's not easy to predict which image has a tumor or which does not have a tumor, even with expertise. So here an AI that is trained on thousands and tens of thousands of such images can actually very accurately predict the presence or absence of tumor. And let's see how we can do that. So again, this project cycle is divided into five different sections: project scoping, data acquisition, data visualization, modeling, and evaluation. So in the problem scoping, basically the objective is to classify brain images into benign, which is non-cancerous, and malignant, which is cancerous. So benign might be even a very, very small minuscule tumor, which does not even show up really well in the image. So now let's start. So firstly, we are looking at data acquisition. So we have data set which includes images of brain scans, which are MRI, X-ray images, and these images are labeled into whether it's malignant or whether it is benign. So let's look at the type of images. So for example, so the data set is actually linked over here. You can click here to see the original source of data set, or you can also click here to download it in the form of a Excel sheet. But basically, if the tumor is not present, it is encoded as 0. If the tumor is actually present, it is encoded as 1. So this looks like malignant, which means this is encoded as 1. You can see there is something here, and this does not have the presence of any tumor. So this is encoded as 0. So this is exactly how the data looks like. Bunch of labeled set of images, which are brain MRI scans. Now, when we continue, let's try to predict if this image shows whether there is a malignant or benign tumor. So I can see something here. So I will try to predict that this is malignant. It may be correct. Yeah, so this is correct. So this is how you can do it. If you try to predict it as benign, it's basically incorrect. So this is how an expert can predict. But this is a relatively simple image. You can suddenly see that this thing is asymmetrically showing up here. But it may or may not be a malignant or benign image, benign tumor. We don't know. But I just predicted based on common sense. But that's not how experts do it. Now let's see how an AI system can do the same. Let's continue to data visualization. In data visualization, we can visualize several different things. Let's start. So firstly, we have training set, we have validation set, and we have test set. So and no means no. It's a benign thing. It's not a problematic tumor, and yes means it is problematic. So let me first have a look at a malignant tumor. So this is malignant. I can just move it here. Here is another malignant. Here is another malignant tumor again. And you can see that it's clearly visible. These are easy to detect images of malignant tumors. Now let me look at benign. It's sometimes not easy to predict whether there is a presence or absence other than for the symmetry. So these images, this one looks very symmetric, but who knows whether this is a tumor or not. We don't know, right? Same thing here. This looks symmetric, so I am tempted to say this is benign. It is actually benign, but there is no proof. Like we can't know unless it is verified by an expert, or unless we train an AI model to be able to predict this with very high accuracy. But it looks to me, with the level of symmetry, it looks like maybe nothing is wrong. This also same, like I don't know what this color over here means. It may be benign, but actually it is benign. So the bottom line here is that it's not extremely easy to predict. For some images, it is probably easy to predict. For example, in malignant images, some of them are easy to predict. So this is probably easy to predict. This is maybe not as easy to predict. We don't know. It does not look like a tumor. It looks like just some kind of smudge. This definitely looks like something. This definitely looks like something, etc. Right? So now in the data set, we can see that here in the training data set, 119 of them are in the yes category, meaning there is tumor. Here it's in the no category. Same for validation and testing. So this is how the count in each of the data set looks like. So it's almost like 80-20. 80 of them, 80% is in the training, 20% is in the validation, remaining in the testing. Now, if we look at an interactive way of visualizing the MRI images, you can just move this cursor. So if you click the cursor at different locations, you can see that this is how the MRI scan of an entire brain looks like. It basically scans the brain in different layers, starting from, and here suddenly you can see that there is a tumor. So in the same brain at this part of the scanning, there is no problem. Tumor is not detected, nothing is visible. But suddenly when you reach here, you can see something here. And when you reach here, there is something even bigger. And again, yeah, there is a big tumor looking thing, and that's the scan. And similarly here, you can click to see the scan at different locations. This is the MRI scanning. In this image, nothing seems to be problematic, at least for me. I'm not sure whether it is malignant or benign, but it looks like the left one, this one is in general malignant. It has a tumor. And the right one, this one in general is benign. It looks at least fine for me. But this is how the image or the data looks like. Now let's move on to the next part, which is cropping the images. So basically in data cropping, we have to ensure that all these unnecessary dark regions are not coming without any point. So basically data cropping is like removing irrelevant information and providing a different perspective. And data normalization is something where we can either normalize the data such that the pixel value ranges from 0 to 1 or 0 to 255, etc. And that helps in the training process. Now let's continue to the next section. Moving on to the next page. This is about modeling. So we'll be training a convolutional neural network, which looks like this. So if you have an input image, it is sent into different layers. So there is an input layer, there are a bunch of hidden layers, then there is an output layer. Final output layer is this, but in between there is a flattened, fully connected, softmax, etc. So a convolutional neural network is a AI or mathematical construct which is used for image classification primarily, but it can be also used for many other things. But the image that is fed is taken according to pixel by pixel, and then it is transformed, and finally it predicts. So in our case, we have input image, which is the brain tumor image. Output is only two, either it is benign or malignant. It's a binary classification. Now there are a few parameters that we have to adjust in the convolutional neural network architecture. One is the learning rate. Learning rate means the rate at which the parameters of the neural network will be modified according to whether there is an error in prediction or not. Epoch is the number of iterations over which the same data will be passed through the convolutional neural network, and the test to train split ratio will be the amount of data set belonging to test to amount of data set belonging to train. So these are the three parameters which are also called as hyperparameters that we will be changing. So let's first adjust the learning rate. So learning rate I'll keep 0.1, epoch I'll keep 2, test to train split ratio maybe I'll keep 80. So 80 is testing, training is 20, and submitting means it will create, it will train the model and it will show the accuracy. Let's see how much is the accuracy. So when you click submit, it takes a couple of seconds for the results to display. You have to wait for a bit. Yeah. So after you wait, you can see that the validation accuracy is actually 61%. The validation accuracy is 61%, and test accuracy is really bad. It is 50%. And test accuracy 50% means you are literally like doing a coin toss for predicting whether it's a benign or a malignant tumor. So what you really need is an accuracy much above 50% for binary classification. If it is below 50%, it's absolutely worst. So we know that these three parameters are not really good for the training purposes. Now let's change the parameters. I'll just click this once again, load the page, and let's select a very low learning rate, 0.0001. epoch, let me keep it as 30, and train to split ratio 20. So this, if we click submit, it's loading the results. Just wait for a little bit. Here nothing will appear for like 1 or 2 seconds. Just wait until the results appear. And here we can see that the validation accuracy is 75% and test accuracy is 80%, which is very, very good for a binary classification. And here this confusion matrix, what it is showing is there are 4 cells in the confusion matrix. 0 means benign, 1 means malignant. So basically here we are predicting 0, but in reality it is malignant. And here we are predicting 0, which is benign, and actually it is benign. And here we are predicting 1, which is malignant, it's actually malignant. And here we are predicting 1, which is malignant, and it's actually benign. So this and this are not good because these are false negatives. These two are true positive. So we need more of the data points in the true positive and less in the false negative. That's when we have a very, very good model. And we can see here that most of them are true positives. Very few of them are false negatives. True positive and true negative are, both are good, but false positive and false negative are not good. So these two are false positive and false negative. These two are true positive and true negative. And you can see that the accuracy is increasing with epochs. So we initially tried with 2 epochs, the accuracy was not good. Now we tried with 20 epochs, but here we are plotting only till 10 epoch. You can see that training accuracy is very, very good, 95+%. Test accuracy is almost close to 80%. So this is quite good in terms of accuracy. But if we change the learning rate to 0.1, epoch to 2, and train test split ratio to test train split ratio to 80, and when we run the model again, we see that model accuracies in the training is actually quite bad. Training and test are quite bad. Both are close to 60%. So it's not a really good model at all. It's like predicting randomly almost. Now let's come to evaluation. So let's run the model again, once again with the proper parameters. Epoch 30, learning rate 0.0001, test train split ratio 20. Then I submit, and this will show the better accuracy. Oh, in fact, let me just run it once again. Yeah, so test accuracy is 80%, which is quite good. So now we need to test on some actual images, whether the test accuracy that we get is good or not. So let's now move on to the evaluation section. So here, each images we'll be testing manually. So first click the first image, click test your model. It's predicting the predicted value and actual value are correct. Now select the second model, test it. It's predicting correctly. Third image. Here there is a mistake. It was actually malignant but predicted benign. Fourth image, correct prediction. So out of the 4, we have already gotten only 1 wrong. Rest of them are correct. So that's almost like 3 by 4. 75% accuracy almost, which is close to the actual test accuracy. Here also we are getting correct prediction. Click this, click test. There it made a mistake. It predicted malignant while it was actually benign. This was correct. It is malignant and actually predicted malignant. And here also there was a mistake. So out of the 8, there were around 3 mistakes. The rest of them were correct. So this is how we can train the model using different parameters and get different accuracies.